Hey everybody, this device here is known as a cathode ray tube. You're probably not super familiar with them from your everyday life. However, you might remember old TVs and computer monitors that had very large backs. They had these large backs because they housed cathode ray tubes, and it was the fundamental technology that allowed them to produce a picture. A cathode ray tube shoots a beam of electrons from one side to the other. At the end of the tube, there's a fluorescent material that lights up when it is struck by an electron. If we turn this on, we can actually see this in action. This green light is the location where the beam of electrons is actually impacting the fluorescent material. In this activity, we're primarily going to be interested in seeing how magnetic fields affect the movement of charges. If an electric charge is passing through a magnetic field, it's going to feel a force. But before you actually watch the experiment, make sure you and your group have made predictions about what you expect the force to be. All right, here's our first example. We have this telegraph key that allows us to easily turn the current on and off and see the effect. In this case, the current that's producing a magnetic field is traveling through the white wire under the cathode ray tube in the same direction as the electrons are traveling. Let's test it out and see what happens. As you can see, the dot was deflected upwards. This means that the force on the electrons in the cathode ray tube from the magnetic field being produced by this wire is up. Case 2 is exactly like case 1, except instead of the current in this white wire flowing in the same directions as the electrons are traveling, it's now flowing in the opposite direction. So what do you expect to happen? Notice that this time the electrons are deflected downwards. This probably shouldn't come as a huge surprise. The current is traveling in the opposite direction, which means the magnetic field points in the opposite direction, which means the force on the particles is also in the opposite direction. All right, here's our third example. Current in this case is going to be traveling down the wire like this. What do you think will happen when we turn it on? Again, we see that the force is down in this case as well. All right, now we're going to move on from producing a magnetic field with a single wire to producing a magnetic field with a coil of wire. In this coil, the current is traveling this way. What direction do you think the electrons will be deflected in this case? Notice there's a fairly large deflection to the right. In fact, this deflection was much more significant than it was for the single wire. Why might this be the case? Well, the answer is that a big loop of wire can create a much stronger magnetic field than a single wire by itself. A stronger magnetic field means a stronger force on the electrons, and a stronger force means a larger deflection. All right, here's our last example. I'm going to try to hold the cathode ray tube directly in the center of this loop. Let's see what happens. Notice there was basically no deflection at all. It's certainly tiny as compared to the effect that the loop had on the electrons in the previous example. So if there was no deflection, then there was basically no force. How could this be? Well, we know that an electric charge feels no force when it is traveling in the same direction as the magnetic field is pointing. And this loop is actually producing a magnetic field in this direction.